Okay, we are discussing about a data structure called binary decision diagram, and this binary decision diagram is used to represent any Boolean function. Okay. Now, today we are going to see some operation that can be performed on order binary decision diagram. Because we have already discussed about say BDD, we have introduced what is your BDD, binary decision diagram. Then we have talked about OBDD, ordered binary decision diagram. In ordered binary decision diagram, we are going to maintain a particular ordering of the variables. Okay. And after that, we have talked about ROBDD, reduced ordered binary decision diagram. That means, this is the reduced form or the reduced BDD of a given particular Boolean function, which follow a particular ordering of the variables. And we have seen one property that the ROBDD of a given function is always unique. That means, it is the canonical representation of a given Boolean function. So, with a particular variable ordering, we are going to get a unique structure, unique BDD structure for that particular function. If we change the BDD, if we change the variable ordering, that we may get another structure. Now, say when I am having say two function f and g, then the BDD representation of f will be of bf and the BDD representation of g will be of bg. Okay. Now, what happens? We can perform the operation f plus g, or we can perform the operation f dot g, or like that f exclusive or g like that. When we have talked about BDD, binary decision diagram, at that time we have seen that we can perform those operations on BDDs also. So, what we have seen on that particular case? We have seen that if I am having a function f and the BDD representation of where f is bf, then bf I can say that this is the structure, and eventually we are having the terminal node 0 and 1. Similarly, I am having a BDD bg of a function g, again I can say that I am having a BDD representation of this function, and these two are the terminal nodes. Okay. Now, when I am going to perform say f plus g, then what will happen? We can perform this operation on BDD. What we can say that this is your bf. So, if your function if value of the function f is 1, then f plus g will be 1, but if value of f is 0, then what happens? We have to now look for the valuation of your function g. So, in that particular case, what happens? We have seen that in this particular 0 node, we are going to put this particular BDD, bf, bg and 0 and 1, these are the terminal nodes. So, if f is 1, then we are going to get that the functional value is 1, and if f is 0, then we are going to look for the what is the valuation of g. Depending on that, I am going to get the functional value for f plus g. Similarly, we can go for f dot g also, but what is the problem that we are going to get over here? You just see that f is a function say which is having some variable say x, y, z. Similarly, g is also a function which is having say variable x, y, z. I am going to say this three functions. So, you just say that BDD bf is an order variable, ordered binary decision diagram. That means, it is having the variable ordering x, y, z. Similarly, that bg is also having variable ordering say x, y, z. But when we construct this particular BDD, in that particular case, what will happen? We are not going to get this ordering of the variable x, y, z, because somewhere here x is appearing and somewhere here also x is appearing. So, in one particular part x is appearing twice, which is the violation of your ordered binary decision diagram. So, that means, if we are simply going to construct the BDD for f plus g by taking the BDD bg with your bf, then we are not going to get an ordered BDD. That means, the resultant BDD is not an ordered BDD. So, for that simply we cannot use this particular operation that we use for your BDD. So, for ordered BDD we have to handle it differently. So, today's lecture we are going to see how we can perform those particular Boolean operation on the BDDs or in particular ordered binary decision diagram. Okay. Now, just see that what we are going to see in this particular case. So, the operation for any kind of operation we are going to use an algorithm called apply. This apply algorithm will be used to perform any Boolean operation on BDDs. So, that means, if we are applying these things on BDDs, we are going to get some resultant BDD, which is going to give us the evaluation of this particular Boolean operator. So, the apply algorithm is going to take two BDDs. Say for f I am having BF1 BDD representation of f and I am having say BG BDD representation of G. Then the algorithm apply will take this particular form. It is having three parameter apply, operation, BF and BG. So, we can give any binary operator over here and two BDD. So, BF and BG are BDD representation and F and G. Now, if I use this particular function apply, say plus BF BG, in this particular case what will happen? We are going to perform the OR operation on Boolean function f and g. So, f plus g, and after that we are going to represent these things with our BDDs or ROBDDs. So, in this particular case we are having the BDD representation of Boolean function f and BDD representation of g. So, we will use this particular apply algorithm to perform this particular addition or OR operation. Similarly, we can use and you can use XOR operation like that. In this particular operator we can use any operator, and this apply algorithm is going to perform or going to give us the BDD, which is going to represent this particular function f plus g or f dot g. Now, while I am going to talk about your f g or f BF, these are the BDDs. So, these are ordered binary decision diagram, and these two binary decision diagram must have computable variable ordering. So, what does it means? In case of computable variable ordering, both the BDDs must have same variable ordering. That means, if one is having say variable ordering x2 like that xn, the both BF and BG should follow this particular same variable ordering. Okay. So, that means, what we said that computable variable ordering, say if I am going to BDD BF and BG. So, in BF, say if x is appearing before y in the ordering, then that should be satisfied in BG also. X must appear before y in BG also. So, for all variables, if it satisfies this particular requirement, then we can say that these the variable orderings are computable for these two BDDs. So, one primary requirement for use of this apply algorithm is that both the BDDs must have computable variable ordering. So, when we are going to use this particular apply operation, we are going to give two BDD BF and BG, and just say that these two are ROBDD, reduced binary decision diagram. After application of this particular operator, so we are going to get say going to perform that plus BF and BG. This particular apply algorithm will return what it will return? It will give me an ordered BDD which represent f plus g, and the ordering of the variable is same with the ordering of BF and BG. So, the resultant BDD is also an ordered BDD, and ordering of the resultant BDD is the ordering of the two input BDDs. But after application of this particular apply operator, whatever BDD we are getting, it may not be a reduced one. Okay. So, after apply algorithm, what we can do? We can use the reduce algorithm to get the reduced ROBDD, reduced ordered binary decision diagram. So, basically what happens? Now, we are going to use apply algorithm, apply say some operator say plus BF and BG. Here they should have computable variable ordering. The resultant of this particular operation will give me an ordered PDD. So, in this particular case the ordering is same with input BDD. Whatever ordering we are having in input BDD, it is going to give me the same ordering. We are going to get an BDD which is having the same ordering. But the ordered PDD that we are getting may not be a reduced one after performing this apply operation. So, to this particular resultant BDDs we are going to use the reduce algorithm. In last class I think we have discussed about this particular reduced algorithm. So, after application of this particular reduced algorithm, whatever BDD we are getting, it will be your ROBDD, reduced order binary decision diagram. That means, if we are having two functions f and g, we can represent these two functions with the help of two ROBDDs. And basic requirement is that the ordering of these two BDDs must be same. That means, they should have a computable variable ordering. After application of this particular apply algorithm, we are going to get a ordered BDD which represent this particular function f of g. Okay. That resultant BDD may not be a reduced one. So, we are going to use the reduced algorithm to get the ROBDD of this particular output OBDDs. Now, how we are going to perform this particular apply operation? Okay. So, this is basically again based on our Shannon expansion only. Say, I have already mentioned that the construction of BDD depends on the Shannon expansion of a Boolean function. So, Shannon expansion we know that it is representing with the help of this expansion. F is a function. So, f can be represented by x bar. F we are going to evaluate f where x is replaced by 0 plus x dot f is replaced by 1. Similarly, g x bar g we are going to evaluate g by replacing x equal to 0 plus x and going to evaluate g by replacing x equal to 1. So, these are the two Shannon expansion of our given function. Now, if we are going to perform any operation f of g, you just see that we can rearrange this particular expansion and what we are going to do x bar, then this part we are going to perform this of operation, that operation on the evaluation of function f replacing x by 0 and evaluation of function g replacing of x by 0. So, we can perform this particular operation on this sub function, because already we have taken the decision of x equal to 0. Similarly, for x equal to 1, I can going to look for this particular thing. So, this operation, you just see that while constructing our BDD, we are going to apply this particular Shannon expansion recursively after one variable to the other variable. So, that same Shannon expansion will be used for performing the operation in this particular apply algorithm. So, from root node we are going to perform and going down to the leaf nodes, step by step. So, it is some sort of your top down approach. We are going to start with the root nodes of the given BDDs, we will traverse it down in the top down fashion and eventually we are going to get the root nodes, terminal nodes or the leaf nodes. And when we are coming to this particular terminal nodes, then what will happen? In terminal nodes, we are going to get the terminal values. So, in this particular case, we are saying that f of c. Now, when we are coming down to terminal nodes, then in case of terminal nodes, we are having the value either 0 or 1. Now, when I am coming to this particular terminal nodes, then I can apply this particular operation, because I know that if my operation is your say dot, then I know that 1 dot 1 is equal to 1, and for other combination 1 dot 0 is equal to 0, or maybe 0 dot is equal to 0. So, like that we are going to construct the resultant BDD, and when we are going to get the terminal nodes, then we can eventually apply the operation on those particular terminal nodes. Now, just see that we are going to do it recursively. Let RF be the root node of our BDD BF, and RG be the root node of BDD BJ. That means, you can say that this is my root node RF, and we are having the BDD, something like that. Okay. Now, I can apply it any levels. Once I take the decision over here, then what will happen? I have to look for this particular two sub BDDs. That means, when I am coming to this particular sub BDDs, then I will say that this is my root node RF. So, that is why in general I am saying that let RF be the root node of BF, and RG be the root node of your BJ. Now, what is the first step? Apply algorithm, apply of BF and BJ. If both RF and RG are terminal nodes, which label with LF and LG. Okay. So, now first condition we are saying that when we are coming to the terminal nodes, this is your two terminal nodes. So, this is I am saying that labels, this is your LF and this is your LG. Now, LF and LG, these two can have values either 0 and 1, nothing else, because these are the terminal nodes and these are the value. Then compute the LF of LG. That means, in this particular case, when we are coming to these things, then we are going to perform the LF operation LG, and the resultant BDD will be B0 if the result is 0, or it is B1 if the result is your 1. That means, I can say that 1 plus 1 is equal to 1. So, in that particular case, I am going to get the BDD 1, which is your B1. Similarly, if it is your 0 plus 0, then it is equal to 0, then I am going to get the resultant value as 0, which is the BDD B0. So, when we both the nodes are terminal nodes, then we are having the evaluation of this particular function. So, we can apply the operation on this terminal node, and the resultant BDDs will be either B0 or B1. So, this is the first case we are going to consider if both are terminal nodes. Okay. Now, if it is not terminal nodes, then what will happen? At least one of the nodes will be your non-terminal node. So, when I am going to talk about say, RF and RG, if both are not terminal nodes, then at least one of them will be your non-terminal nodes. Now, first case we are going to consider that if both nodes are xi nodes. So, both are xi node means both nodes are your non-terminal nodes, and they are labeled with this variable xi. Okay. Now, we are going to create a node xi. That means, since now both the function are depends on this particular variable xi, we are going to create a node xi, and we label this particular node, or we are going to call this particular node RF and RG, because in my given BDDs, one node is RF and second node is RG. So, we are going to label a node called RF and RG, and since both these particular nodes are labeled by xy, we are going to construct a xi node, and after that, when I am having this particular xi node, this xi node has two edges, one is dashed and one is your solid. Dashed line will say that xi equal to 0, solid line will say that xi equal to 1. So, in that particular case, we are going to apply this particular operation for your dashed line of LO RF and LO RG, apply OF high of RF and high of RG. So, basically what will happen if this is my RF node, then I know that I am having two functions already we have defined. One is your low RF and second one is your high RF. What it will return? Basically, it will return the nodes that is pointed by dashed line. In case of LO, say if it is said that this is my say P Q, that means LO RF will return P and HI RF will return Q. That means, now when I am going to perform the operation on this particular RF and RG, Next time what will happen, by looking into the evaluation, we have to take decision on these two nodes P and Q. That is why we are applying these things of LO RF, LO RG, and in solid line apply OF of high RF, high RG. So, whatever we are having, so this is what is the dashed line and what is the solid line, what is the decision, we have to look for those particular sub BDDs. So, that is why we are saying that we are going to apply the operation on low of RF and low of RG, and in case of high of RF and high of RG. So, if both are labeled with same variable xi, then we are going to follow this particular rule. Now, on the other hand, in the second case what will happen, we may have one non-terminal nodes or one terminal nodes also. So, in this particular case, say RF is having an xi node and RG is having an xj node, where say j is greater than I. So, in while we are traversing it from top to bottom, when we come to this particular scenario, one is xi and one is xj and j is greater than I. Basically, it says that this particular BDD Bg will be independent of this particular variable xi on that computation part, because we are traversing it from top to bottom and uniformly we are going down. In one part we are getting xi, but second part we are not getting xi, we are getting xj. So, what does it mean? That means your Bg is independent of xi in that particular evaluation part. So, for that what will happen now, the resultant BDD now may be dependent on xi, because one of the function is dependent on xi. So, we are going to create an xi node at that particular point, and again similarly it will be labeled by RF and RG, because these are my root nodes, and similarly we are going to construct this particular two nodes. So, what will be the position over here? You just see that we are going to now apply this particular operation OP low of RF and RG, because RG is independent of your xi. So, that means again I have to look for down the line somewhere I am going to get xj in your RF. At that time I am going to see what will be the situation. So, that is why we are going to apply LO RF and RG, because RG is your independent of I, and in case of your solid line we are going to apply of high of RF and RG. So, this is the way I am going to construct my resultant BDD. So, here RF is an xi node, but RG is a terminal node or it is an xj node. Here I am talking about it is an xj node, j is greater than I, or it may happen that RG may be your terminal node also, then the treatment will be same. We will see in that case what we are going to do. So, this is the second scenario, and third scenario is when I am saying that if RG is the xi node, but RF is a terminal node or xj node where j is greater than 1. So, this is basically, if you see, this is symmetric to this particular condition only, but now situation is different. What we are saying that RF, it is a xj node or terminal node, and RG is an xi node, and here it says that j is greater than I. So, this is similar situation like the previous one, but in that particular case we are saying that RF is an xi node, but now we are saying that RG is an xi node. So, this is the similar situation. So, here that in similar way we are going to treat it. So, in dash line we are going to say that of LO RG and RF and apply of high of RG and RF. Just see that these are symmetric. So, that is why we are taking, in the previous case we are taking LO RF and RG, now we are going to take LO RG and RF. So, these are the rules that we are having over here. Now, just see that we are going to take two ROBDDs, we are going to traverse it from top and it will be a top down approach. If both are terminal nodes, then we are going to apply the operation over there, because we know the values, either it will be 1 of 1 or 0 of 0 or 1 of 0 or 0 of 0. We may have 4 conditions. In all other cases, one of the node will be your non-terminal nodes. One situation is happening, in both the non-terminal nodes are having the same level. We have seen what we are going to do. In the second case, one is a non-terminal node, second may be a terminal node or another non-terminal node, but their level is not same. So, we have seen how it is going to, or how we are going to handle this issue. Now, this apply algorithm we are going to now see with the help of an example. Just see that this is one BDD, so for function your f. So, I can say that this is your BF and say this is the BDD for function g. We can say that this is your BG. Okay. Now, both are having the same variable x1 to x4, okay, and the variable ordering is your x1, x2, x3, x4. By looking into this construct of these two BDDs, we can find that, we can see that they are having the computable variable ordering, they are following the same variable ordering. Now, I want to perform f plus g. Okay, so, this is, that is why I am saying that this BDD plus this BDD is going to give me f plus g. Now, what we are going to do? Now, we are going to start from the top. So, I will consider these two are my root nodes as my nomenclature. This is your RF and this is your RG. Now, we are having the nomenclature over here R1, R2, R3, R4, R5, R6, R7, S1, S2, S3, S4, S5. Okay. Now, see what we are going to construct. First, we are going to take this particular root node. Okay. Now, I am going to take R1, S1 and you just see that both are having the same variable level x1 and x1. So, we are going to create an x1 node. So, low of your R1 is going to R2 and low of x1 is going to S4. Similarly, high of R1 is going to x2 and high of S1 is going to S2. So, that is why we are constructing this particular structure R1 S1, it is labeled with your x1. Now, it is R2 x4 and R3 S1. Okay. So, this is the scenario that we are having. So, we are coming to this particular thing R3 x1. Now, after that what will happen? Now, that means I am going to look for, if I am going to follow this particular dashed line, this will be my root node and this one will be my another root node. Okay. Now, I am having this partial structure. Now, in this particular case, now R2 is a root node and your S4 is a root node. So, one is your non-terminal node, second one is a terminal node. So, in this particular case, what we are going to do? We will, for dashed line, we will follow this low of this one and it will remain as it is. For your this thing psi 1, it will follow this structure and it will remain as it is. So, in this particular case, if you look into it, we are going to apply this particular rule. Already we have discussed that low of RF RG, high of RF RG. So, we are going to get this structure from R2 S4, we are getting R4 S4, R5 S4. Okay. Similarly, if we look into the other side for 1, so this is my root node and this is my root node. So, we are going to construct an S2 R3. So, this is your S2 R3 and these are the dashed line is coming to R5. So, both are non-terminal nodes and we are going to get an X3 node over here, because you just see that this is your X2 and this is your X3 and this is also X3. So, I am going to create an X3 node over here and we are getting this particular two dashed line and solid line. Now, R4 S4 and R3 S4 and R5 S3 and R2 S6. So, in this particular case now, by considering these as a root node, this one will be one root node and this one will be the another root node. So, we are going to construct this particular dash line and solid line. Similarly, here we are getting whatever may be these things. So, we are going to have this scenario. So, now we are coming up to this particular level. Now, when we are constructing, say from top R 1 S 1, we are starting it and coming down this. Now, you just see that all those particular nodes, whatever we are getting over here, all these things are now terminal nodes. Now, I am going to apply the binary operator on these particular terminal nodes. Okay. Now, while I am applying this particular terminal nodes, you just see that 0 plus 0 will be 0, something like that, 1 plus 0 will be 1. So, basically you just see that this is your R 4 S 4, R 7 S 4, okay. R 7 S 4, R 7 is 1, S 4 is 1. So, 1 plus 1, it is going to give me 1. So, in this particular case I am going to get 1. So, eventually I am getting this particular structure. Okay. Now, this structure, now what will happen? Now, I can construct the BDD from this particular structure. I am getting, say this is your x 1, this is the dashed line, this is solid line. In dashed line I am getting x 2, in solid line I am getting x 3. Okay. Now, in this particular dashed line I am getting your x 4, and in this solid line I am getting this particular x 5. Okay. Like that I am getting this particular dashed line and this solid line. So, this solid line will come to 1. So, like that I can construct the BDD. So, I am getting an BDD and this is basically OBDD. I am getting this OBDD from this particular structure. Now, after getting this particular ordered binary decision diagram, we can see that it may not be a reduced one. So, after that we are going to apply this particular reduce algorithm, and after applying of this particular reduce algorithm we are getting this particular structure, and this is the ROBDD that we are getting over here. So, eventually we are getting ROBDD for f plus g, and the ordering of the variable is same with the ordering of your bf and bg. This is basically x 1, x 2, x 3, x 4, where bf is the order BDD or ROBDD of f and bg is the ROBDD of g. So, what happened? We have used this particular apply algorithm plus bf, bg, and we are getting this particular ROBDDs, BDD for f plus g. So, like that, if we are having two ROBDDs, we can always use some binary operation on these two structure, and we can eventually get the ROBDDs to represent this particular Boolean operation. Okay. So, this is one important algorithm, and we will be using this algorithm while going to look for the uses of ROBDDs. Now, another issue we are going to see that we have seen that apply algorithm. Now, we are going to look for another issues. We said that a Boolean formula obtained by replacing all occurrence of x by f, x or in f by 0 is denoted by f x replaced by 0. That means, if I am having any Boolean function, say f is equal to say x y bar plus x dash z plus x y z, something like that, I am having a Boolean function. So, basically this Boolean function depends on the valuation of x, y and z. X may be either 0 or 1, and similarly y and z. But we can say that what will be the valuation of this particular function when I replace all x by 0. So, this is basically we are denoting these particular things, all x replaced by 0, what is the functional value. Similarly, we can say that what is the functional value if I replace all x by 1. That means, we are putting a restriction on one variable. I am saying that x will be always 0 only, or we will say that x will be always 1 only. You just look for the valuation of this particular function depending on the other variables. So, this is the way we can look into it, and we can say that this is basically known as our restriction of f. Okay, we are going to say that we are going to restrict the valuation of function with respect to some variables. I am having a variable or function which depends on several variables, but I am saying that restrict that particular function for one particular variable to be 0 or restrict that function for a particular variable to be 1 only. So, we are going to say this is the restriction of this particular function f. So, we are going to have restriction of this function f, f x is replaced by 0 or x is replaced by 0. Now, if we are having BDD representation of f say b f, whether we can directly restrict it or not, we can apply this particular restriction on it or not. So, here I know that if I am going to restrict it for x equal to 0, then we will find something like that, it will be o z only, because x dash 0, other two terms will be 0. So, similarly, if I am having the BDD representation of this Boolean function f, whether can I apply this particular restriction on those particular Boolean function or not. So, it is very simple. So, what happens? We are going to say that this is restrict 0 x b, and this is basically nothing but f replacing all variable of all x to be 0 and restrict 1 x b f. This is nothing but restriction of this Boolean function f replacing occurrence of all x by 1. So, if I am having the BDD representation of this particular Boolean function as b f, it may be a reduced ordered BDD also, then with the help of this restrict operation or restrict algorithm, what we can do? We can construct the f x replaced by 0. So, what we are going to do in this particular case, we are going to look all nodes corresponding to this particular label x. Okay. So, we are going to look for all corresponding nodes that are label x, and we will remove all such n, and we will redirect the incoming edges to low of n, because why we are redirecting the incoming edges to low of n, because we are restricting x to be 0. So, basically if I am having an x node over here and say these are your low and this is your high. Okay. So, we may have some error. So, when I am going to restrict x to be 0, that means x will be always 0. So, this evaluation we are not going to consider. So, in this particular case, we are going to remove this particular node, and whatever incoming edges we are having, all those will be redirected to this particular low node. Similarly, we are going to use this particular restrict 1 x b f. So, the treatment is similar. Now, we are going to remove all those particular node labeled by x, and we are going to redirect the incoming edges to high of n. Okay. So, this is the way we can construct ROBDDs for our restrict operation also. We are restricting the function where x will be 0 and we are restricting the function x will be equal to 1. Okay. So, we can, if we are having a BDD representation of a Boolean function, we can construct the restrict O 0 x b f by removing the all x naught from this particular BDD and redirecting the incoming edges to the low of n. Okay. Similarly, for restrict 1 x b f. So, we are talking about some functions, say if I am having f x y z. So, something like that x y plus y z. So, in this also y bar z. So, in this particular case what will happen? This is a function depends on these 3 variable. So, we are saying that sometimes we restrict that particular function on a particular variable, that variable will be either equal to 0 or that variable will be equal to 0. Sometimes we want to relax the constraint on some variable. What is this particular function? Basically, we are saying that the functional value will be 1 provided x is equal to 1 and y is equal to 1, or y is equal to 0 and z is equal to 1. So, the function value will be 1 provided it satisfies this particular constraint. Sometimes we want to relax the constraint on some variable. So, you just look into a particular function or look into the function that derived from this particular given function where it is independent of one particular variable. That means, we are going to relax the constraint of this particular function on a particular variable. So, we can relax the constraint of some variable of x for this particular Boolean function x. That means, the functional value will give me the evaluation 1 either x equal to 0 or x equal to 1. Whatever may be the value of x, that function is going to give me a valuation 1. That means, the valuation will depend on other variables. So, in that particular case, we are going to say that we are relaxing the function on a particular variable. Okay. Now, generally we write these things with the symbol dr exists f, where we say that we are relaxing this particular function on this particular variable x. That means, we say that there exists a variable x where the constant is relaxed. Okay. Now, this is expressed as with this expansion. There exists x f. It says that we are going to relax the constraint on x for this particular function f. This is f, either x will be replaced by 0 or x will be replaced by 1. That means, x can whatever may be the value of x, now we are going to look for the functional value of this given function. So, it is very simple. What is the Shannon expansion? Basically, we are going to say that if x equal to 0, then we are going to say that evaluation of f with respect to 0 or x equal to 1, evaluation of this particular function by x equal to 1. Now, I want to relax the function either x equal to 0 or x equal to 1. That means, we are not considering the value of this particular x over here. So, we are dropping these two x bar and x. So, we are saying that f of x equal to 0 plus f x equal to 1. So, whatever may be the value of x, now going to look for the functional value of the given function. So, this is relaxing on this particular variable x. So, we are saying that there exists an x on which the constant is relaxed, and we evaluate this particular function with the help of this expression. Sometimes we relax the function on some variable. So, we relax the constant on some variable. So, this is the way we are going to do it. So, with this expansion we can evaluate this particular relaxation. Now, if we are having the BDD representation of this particular Boolean function, so whether can we use this particular relaxation on this particular BDDs or not. So, if we are having the BDD representation B f of a given function f, then how to find the relaxation on a given variable x. Already we have seen this restrict operation on restrict algorithm. We are with the help of this restrict algorithm, we are restricting the function to a particular valuation, either x is equal to 0 or x is equal to 1. But in case of exist or relaxing on that particular constraint, it may be either 0 or it may be 1. So, that is why we can evaluate this particular dr exists x f with the help of this particular expression, using this particular relax operation, restrict x to be equal to 0 and restrict x to be equal to 1. So, in case of relaxation, we are going to say that x may be either 0 or 1. So, that is why we are using this particular OR operation plus operation. So, we are using apply plus restrict 0 x b f and restrict 1 x b f. Now, you just see that we are using this particular restrict x to be 1, restrict x to be 0. So, if I am having say RO BDD of B f as your BG. So, after restricting I am going to get one OBDDs. So, and second this restrict operation will going to give me another OBDD. Okay. But the variable ordering of these two resultant OBDDs will be same with this particular B f. Now, we are going to apply this particular operation plus in the apply algorithm. So, the resultant will be another OBDD. So, I can say that this is your B 1 and say this is B 2. So, I am getting OBDD B 1 and OBDD B 2. After performing this apply operations, I am going to get another BDD say B 3. So, this is the B 3. Now, it may not be a reduced one. So, to the resultant BDD, I am going to use the reduce algorithm. So, eventually I am going to get the RO BDD. So, the order of the variable of this particular BDD is same with the order of this particular BDD BF. Okay. So, this is the way that we can find out the restriction on some variable. So, this way we can find out the restriction of this particular given function f. Now, this particular exist operation can be nested also, or it can be given as a sequence also. So, basically if said that if I am having a function f on some variable x 1, x 2, something like that x n. So, what will happen, say if I am having say there exists x 1 f, that means we are relaxing this particular function on variable x 1. So, we are going to get one function f which is now independent of x. Now, we are getting one function. Now, what will happen to this particular function? Again, I can put a relaxation on the second variable x 2. Okay. That means, whatever resultant function I am getting, I am going to now put another relaxation on this x 2. Okay. So, again I am going to get another Boolean function. Again, I can put a relaxation on this particular Boolean function, say on the third variable x 2. Like that, we can keep on relaxing it on some function. So, we can use as a sequence. So, we are going to use this particular expression that it is relaxing on say x n, x n minus 1 like that. So, what will happen if f is going to represented by the ordered BDD B f. So, this particular result there exists x 1 f 1 will give me another OBDD. So, to this particular OBDD, I am going to relax on x 2, I will apply this same operation over here and which is going to give me another OBDD. So, like that I can keep on applying this particular operation on this particular resultant OBDD. Okay. So, we have seen some algorithm till now. So, first what happens? We have seen that BDD binary decision diagram, then eventually we have come to the ROBDD, that reduced order binary decision diagram. Okay. Now, what will happen? We are going to get an unique representation of this particular ROBDD for a given function. So, now to work with those particular ROBDD representation, we have seen some algorithms. So, what are the algorithms? First algorithm we have talked about reduce. With the help of this particular reduce algorithm, we can get a reduction of a given variable say B f. So, it will going to return me these things. Then we have seen another algorithm which is your apply. With this particular apply, we can use any binary operation on two BDDs B f and B g, and we have seen that this particular apply operation is going to give us an BDD which is going to talk about the f of g, and one main constant on this particular apply algorithm is that B f and B g should have computable variable ordering, and whatever resultant BDD we are getting, that BDD will have also have the similar ordering with B f and B g, but the output BDD may not be a reduced one. So, we can use after that we can apply this particular reduce algorithm to get the ROBDD. We have seen another distinct algorithm which is your restrict. We can restrict the function on some variable to be 0 or 1. So, I can say that restrict 0 B x B f, or we can say that restrict 0 1 x B f. Okay. So, this is the restrict operation that we are getting over here, and we have seen another algorithm which is exists. Basically, we are going to relax the function on a given variable. That means, we are relaxing the constant on a given variable, or it may be a series of variables. So, these are the algorithm that we have seen which can be directly used on your ROBDD, and resultant we are going to get another ROBDD as a result, where the ordering of the output BDD will be same with the input BDD. Now, just look in the simple question over here. I am saying that consider this particular Boolean function. So, I am expressing a Boolean function. Now, construct the ROBDDs for this particular function f. Say we are going to say that B f. So, I am giving a function f which depends on 4 variable x 1, x 2, x 3, x 4. First, we are going to say that construct the ROBDD for B f, reduced order binary decision diagram. Then look for the structure of restrict 0 x 4 B f. That means, we are restricting x 4 to be 0, or restrict 1 x 4 B f, or restricting the B f where x4 to be 1, that means you are restricting a function f where x4 is equal to 1. So, construct the BDDs and after that you look for this particular function exist x4 bf, that means we are relaxing the constraint on the variable x4 for in the given function x. Okay. Just see what the BDD bf will look like. You can use the Shannon expansion to construct this particular BDD. Here I will just give you the resultant BDD. Okay. So, this is the arrow BDDs for this particular given function and the ordering that we are going to consider is your x1, x2, x3, x4. Okay. So, by using the Shannon expansion, you can construct the OBDD and after that apply the reduce algorithm to get the arrow BDD and eventually you will get this particular structure. I am saying that with a given variable ordering we are going to get the unique representation. So, if this is your ordering, you are always going to get this structure. So, what is the first term x1 prime x2 x4, that means x1 equal to 0, x2 equal to 1, x4 equal to 1, the function will give me the value 1. Similarly, x1 x2 bar x3, x1 x2 bar x3, it will give me valuation 1, x1 x2 bar x3 bar x4. So, this is another 1 valuation and x1 and x2. So, this is the OBDD representation of this particular given function and you can check that none of the reduction rule can be applied over here. So, you can say that this is the ROBDD of this particular given function. Now, what I am talking about, first we are saying that apply the restrict operation over here, restrict 0 x4 bf. So, what is the rule? Since we are going to restrict this function on a variable x4. So, we are going to look for all x4 nodes and we are going to remove this particular x4 node from this particular BDDs. So, we are going to remove this particular x4 node. When we are going to remove this x4 node, then its outgoing edge will also be removed. So, these two will be removed. And now, we are going to restrict it x4 to be equal to 0. So, we are going to see that one x4 all incoming edge should be restricted, redirected to this particular dashed line. So, this dashed line is redirecting to 0, that means this dashed line will be redirected to this particular 0 and x4 is equal to 0, it is redirected to 0, that solid line will be redirected to this particular 0. So, that means after removing this particular portion, we are getting this particular BDD. And if you look into it, this particular now, this may not be a reduced one. Now, we are going to look for whether reduction can be possible or not. What you will find that you will find that this x2 is an redundant node, we are having redundant test. So, we can remove this particular x2 also. So, this is application of the reduction algorithm. So, eventually, we are getting this particular BDD. x1 is 0, then it is coming to 0, x1 is equal to 1, then going to take decision on x2, then 0 and 1, then going to take decision on x3. So, this is the ROBDD for restrict 0 x4 x3. Now, similarly try to construct the BDD for your restrict 1 x4 bf. So, in that particular case what will happen? Similar rules we are going to apply. What we are going to do? We will remove this particular x4 and whatever incoming edges we have, that will be redirected to this particular one edge of this particular x4. So, that means that one will straight away come over here and this dashed line will come over here. So, we are getting removing these things. So, whatever resultant BDD we are getting, it may not be a reduced one. Now, just try to see the rules. Now, when I am coming to this particular x3, then we are getting that it is having a redundant test. So, we can remove it. After removing it, what will happen? That incoming edges will be redirected to over here. Again, when I am going to look into the x2, we will find that this is another redundant test. We are going to remove it. So, after removing it, that one edge solid edge will be redirected to this particular one. So, eventually I am getting this particular structure. So, this is basically structure for your restrict 1 x4 BF. So, this is we know the BDDs for this particular given function, and we are now getting the BDDs or OBDDs, or even I can say that ROBDDs for restrict 1 x4 BF and restrict 0 x4 BF. Once I am giving this particular two BDDs, then always I can look for the exist, there exist x4 f. That means, and it is going to evaluate these things with the help of this particular expression apply plus this restrict x4 to be 0 and restrict x4 to be 1. So, that means, I am having these two operations for restrict 0 and restrict 1. So, in that particular case what will happen? The root node is your x1 node. So, in that particular case I am going to create an x1 node, and so what is the labels? I can say that this is your R1, R2, R3, R4, R5. So, this is your S1, S2, S3, S4. So, I am going to create an x1 node, and I am just calling that this is your R1 S1. Now, this dashed line will go, and we are going to construct a solid line. So, dashed line where it will go? Low of this is R1. So, this is your R2, and this is your low of your S1 is your S2, and in your solid line high of R1 is your R3, and high of S1 is your S4. Now, you just see that this is your R2 S2 and R3 S4. Now, you just see that R2 is a terminal node, S2 is a non-terminal node. That means, now since it is a non-terminal node, so we are going to create a node x2. Similarly, here R3 is a non-terminal node, but S4 is a terminal node. So, we are going to create an x2 node at that particular point. Now, similarly, I have to look for what is the solid and dashed line. So, like that you can now use this particular apply algorithm, and you can construct this particular BDDs. Okay. Now, after that we are going to get the resultant BDD. It may not be a reduced one. Now, after that apply the reduce algorithm to get the ROBDDs or this particular exist x4 f. Now, what will the structure look like? So, you can find that eventually I will get this particular ROBD. You test it, that this is your there exists x4 f. The ROBDD representation of this particular given restriction there relaxation there exists x4 f. Okay. So, what will happen after getting this BDD? You try to construct it, and whatever you are going to get, you apply the reduce algorithm, and eventually you are going to get this particular ROBDD. Now, just have a quick look on this particular problems or question. So that the formula there exists x f depends on all those variables that f depends upon except x. So, we are having a function f, it depends on some variables, say x1 to xn, or say some variable x, y, z, like that. Now, there exists x f. What does it mean? We are relaxing this particular function on some variable. So, now basically what it is asking, that there exists some x f depends on all those variables that f depends upon except x. Now, you just try to get the feeling what that there exists x and see whether this is correct or not. If it is correct, you establish it, or if it is not correct, then also establish it or give an counter example. I think it is a very simple one. Second one is saying that if f computes to 1 with respect to a valuation v. Say if I say that if f is a function x, y, z, w, like that, I can have the evaluation of this particular function, say x equal to 1, y equal to 0, z equal to 1, and say w equal to 0. So, with respect to this valuation, I am going to have some valuation of this function. So, if these valuation compute once, then what it is saying that then there exists f computes 1 with respect to the same valuation. Now, what we have to show that there exists x f will also compute 1 with respect to the same valuation. I think you might have got the feelings, yes, indeed it is going to compute once. Why? Because there exists x f, in this particular case we are going to relax the constant of x. So, whether x equal to 0 or x equal to 1, it is immaterial. So, if for a particular valuation, if f computes to 1, then there exists x f will also compute to 1 with this particular same valuation, because there exists x f is now immaterial of this particular x, whether x equal to 1 or 0. Since x equal to 1 is going to give me 1, so on relaxation also it will give 1. Okay. So, with this I will conclude my lecture here today.